Hello everyone. In this presentation I want to report on the status of our work on the structural properties of chord inventories and chord progressions of traditional Georgian polyphonic vocal music. The specific goal of today's talk is to discuss the determination of the region of origin or the genre of a traditional Georgian song based simply on a digital score. What I would like to emphasize at this point is that, for reasons which I will explain, our work is still very much a work in progress. I should also mention that this project has a long prehistory. The first steps in the direction of our present work date back to the work of Aron and Vallejo from the year of 2008-2010. At that time only Simcha Aron and Frank Kane had met. Then, between 2010 and 2015, Frank Kane and Frank Scherbaum, Simcha Aron and Frank Scherbaum, and Simcha Aron and Florent Caron-Darras started to work together. This led to a first series of short studies of subproblems of our current work, which helped us to identify some of the major hurdles we are facing. The first major problem, which we can only solve to our satisfaction today, is how to deal with the fact that the tonal organization of traditional Georgian music does not correspond to the 12-tone equal temperament system on which Western notation is based. It took several acoustical studies and the exploration of a number of conceptual dead ends, such as the determination of Western church modes, before we found the current work approach. The second major hurdle which needed to be overcome was that before Anna Lulashvili joined the team in 2021, there were no Georgians on the team, and we were therefore worried that our working hypothesis, for example, what are essential and what are ornamental aspects of a piece, or what are the tonal centers and or reference note, might not stand up to the rigorous questioning from our Georgian colleagues. Our current pre-processing workflow consists of several steps. First, cleaning of the digital scores. This consists of separating the three voices of the song onto different staves, removing extra notes such as ostias, trills or appoggiaturas, so that the cleaned scores contain only the notes from the three voices, one per stave and nothing else. This is purely a technical pre-processing step, which, however, requires great care and can become rather time-consuming. Second, reducing the scores to their harmonic pillars. This involves removing ornaments, leaving only structural chords, and also removing invisible notes in digital scores. Third, the scores were exported to musicXML. The next step in the pre-processing chain involves correction of the digital score for its representation in an inappropriate Western 5-line staff notation, which is intrinsically based on the assumption of a 12-tone equal temperament tuning system. In the context of our work, we avoid having to decide on a particular musical scale. We instead make the assumption that A, the melodic scale is heptatonic, with an unknown exact interval structure and sense, and B, that if we remove the accidentals and take the differences of the scale degrees between two voices, we obtain the corresponding harmonic interval. In order to allow for comparison of the relative bass voice scale degrees, we define the scale degree of the ending bass note after accidental removal as 0, scale degrees below that with negative numbers, and scale degrees above with positive numbers. And this is simply for convenience to make the scores mathematically easy to compare. Here is an example. If the scale degree of the individual voices are -1, 3, and 4 for the bass, middle and top voice respectively, the resulting chord would be written as -1, 4, 5. Here the first number corresponds to the bass voice scale degree, and the second and third numbers are the intervals from the bass to the middle and from the bass to the top voice respectively. I should also mention that for purposes of our analysis, for now we ignore the duration of the bass notes. Here you see an example for an original score on the left, and after it has been reduced to its harmonic pillars, which was done by Anna. This concludes the discussion of the conceptual part. Finally, the scores are exported to musicXML files. The computational part essentially starts with the musicXML file. After algorithmic accidental removal and determination of the reference note, the chord progression sequence was calculated and displays as a table. This table was then used for visual quality control, which was done by comparing the chord progression sequence with the score. If the quality control test failed, we had to go back to the algorithmic accidental removal part to identify the reason and modify the algorithm. It took a number of iterations until we had a stable algorithm. Algorithmic accidental removal is not as trivial as it might look at first glance because of harmonic tritones, 600 cents in some scores, which can lead to two different intervals if one wants to determine the type of harmonic interval from the interval size in cents. Once the quality control test is passed, we go to the next steps. Here you see the chord sequence again. For the subsequent processing, we use only the bass degree, B-DEG, and the intervals between middle and bass and top and bass voices. So we end up with a table which contains only 3 different rows. In chord notation, which we do in a subscript-superscript form, this then becomes a sequence of chord symbols. This is not the only way chord symbols can be written, but it is one which for some of us is very intuitive. Here you see the sequence of chord symbols for our running example again. What I'll try to illustrate next is how we can convert this sequence into a sequence of words without losing any information. The reason for doing this is that we then have a lot of tools at our disposal which can help us to understand the syntax of the chord progression. We can do this simply by replacing the subscript-superscript notation by linking the individual components of the chord with underscores, so that each chord symbol becomes a single text string of 13 characters. Of a yet unknown language, I have to say. Formally, however, which means for the computer, this can now be treated like any sequence from a real language. Here you see the sequence of chord signals again. What can we do with such a sentence? Not much with a single sentence, but if we have lots of them, the computer can learn the syntactical structure of the unknown language. For this purpose, we can exploit now the numerous tools which are available in the fields of machine learning or computer linguistics. As an example, here you see a collection of tools from the Wolfram programming language for this kind of analysis. However, usually this kind of analysis is based on large amounts of high-quality data. Therefore, we have been working intensely during the last year to build a database of sufficient size to be able to apply these tools for our purposes. For each song, the chord sequence and the related metadata after preprocessing become an entry in this database. Currently, our complete database consists of 182 songs from different regional subsets. Most of them, 56 to be precise, come from Katli Kacheti, 35 from Guria, 20 from Shemokmedi, 20 from Gelati, 19 from Samekrelo, 15 from Imereti and 11 from Svaneti. Of course, many more scores from these regions exist, but we have not fully prepared them for analysis yet. This is a very time-consuming, partly manual process, which fortunately has only to be done once. And we know that our dataset is still very small for machine learning, but it is already big enough to illustrate some of the emerging possibilities of computational approaches for ethnomusicological research. The single question which I will address in the rest of this talk is the following. Given that we have these 182 songs from 7 different subsets, can we teach the computer to recognize the originating subset of a song simply from the information intrinsically contained in a chord progression? This is a typical classification problem similar to the recognition of a language from a sentence. Automatic language recognition works very well nowadays, as you can see from the following example. Here I have fed the language identifier algorithm in a number of small sentences in different languages. The house is blue, la maison est bleue, la casa est azul, just to name a few. And as you can see below, in this case, the algorithm, which is implemented in the Wolfram language, works already extremely well. Actually, it works perfectly in this case. However, the corresponding classifiers have been trained on millions of training data. And this, of course, we don't have. So let's see how our mini dataset actually works. Actually not too badly. What you see here is the so-called confusion matrix for a so-called Markov model classifier which was trained on our mini corpus. The column entries correspond to the actual classes, while the row entries correspond to the predicted classes. For each of the actual classes from Gelati to Svanetti, one can see how many of the examples were classified correctly and how many classified wrongly. For example, for Gelati, all 20 examples were classified correctly as Gelati. For Guria, of the 38 examples, 36 were correctly classified, one was wrongly classified as Samikrello, and one wrongly as Svanetti, and so forth. You can see from the diagonal, from the large numbers in the diagonal, that the actual performance is pretty good. The overall performance of the classifier can also be expressed by its accuracy, by how many of the examples are correctly classified. And in this case, it's 94%. This means 94% of all the songs which we trained the classifier on are put in the right class. What is even more important is the accuracy baseline, which is in this case 32%, which means that if the assignment would be randomly done, only 32% would be correctly assigned on average. This means the classifier here is 3 times as good as random. Well, although these results look very good, they do not mean that this classifier will also correctly identify previously unseen songs with the same accuracy. To determine the accuracy for completely new data, one needs to split up the already small dataset into a training part and a test part. If we use 10% of the data only for testing, but not for training, the mean accuracy drops down to 56%, which is not surprising at all given the small size of our dataset. However, it's still twice as accurate as the accuracy baseline based on random assignments. This means that the chord progression indeed contain information about the originating subset, and the classifier actually has some predictive power. We can see this qualitatively also from the shape of the confusion matrix, because although the image is blurred, one can still clearly see that the diagonal of this matrix contains higher values than the off-diagonal elements. An ideal classifier would have non-zero elements only on the diagonal. So overall, this is quite encouraging, because the classifier obviously learns something from the chord progression sequences. However, we are not only interested in what the classifier learns. This is often the dark side in machine learning, that people develop powerful algorithms, but nobody understands how the algorithm comes to its result. It is actually us, the humans, who want to understand the syntactic structure. Therefore, I feel that we need to understand how and what the classifier actually learns. Therefore, in the few remaining slides, I'll try to explain in very simple terms how our classifier actually learns and how we can make use of this knowledge for our own understanding. The method which we have used for this illustrative example is based on a so-called Markov model and the analysis of so-called n-grams. This sounds more complicated than it is. An n-gram is simply a sequence of n neighboring elements, in our case, in the sequence of chords. The sequence of chords themselves can also be called a sequence of unigrams. The sequence of 2 neighboring chords would be called a sequence of bigrams. And the sequence of 3 neighboring chords would be called a sequence of trigrams, and so forth. So let's look at the chord sequence for our running example again. Below on the left, you now see the unigrams in this song displayed as a so-called word cloud. In a word cloud, the size of each symbol is made proportional to its frequency of occurrence in the song. So here, the size of the chord symbols is proportional to how often it occurs in this song. So -157, this chord is the most frequently occurring one, followed by -137, and so forth. On the right now, you see the sequence of bigrams, so the chord transitions for the same song, for our running example. And in this case, it's -137, going to 015, so to the finales, and a fifth on it, which is the most frequent chord progression in this song. And you can see, if you know this song, is Tres Samto Man Madelman, this corresponds to the cadenzas in the individual phrases. This is just to illustrate that the n-gram distribution contains syntactical information. Now one can play the same game for the complete corpus, or as done here for the different subsets of it, gelati, guria, imereti, etc. Here for the unigrams, and one can immediately see, for example, that guria, imereti and katli kacheti have the same chord, which is the most frequent one, namely -135. Here you see now the distribution for the bigrams. Now, although the most frequent chords are the same for guria, imereti and kacheti, the most frequent chord transitions are not. So there's a lot of information in these plots, which I do not want to go into detail for the lack of time now. What is relevant for us is that these word clouds are actually probability distributions which tell us how likely is it to observe a particular n-gram given that a song comes from one of these subsets here. So what does the classifier learn? It's the probability that a particular n-gram which occurs in a song comes from a particular subset. And this is simply a bookkeeping exercise for the computers, which computers are very good at. As a consequence, for each regional subset, the likelihood that a particular song belongs to this subset is simply the product of the probabilities of all the n-grams in it. And for the running example, these are shown here. We can see that for most of the subsets, these are very small numbers, 10 to the minus 46, 10 to the minus 92. This is essentially 0, except for one, which is the correct one, namely Shemok Medi. Okay, but what can we learn from these classifiers? Well, there are trivial things which we can learn. And so, for example, we can easily determine what are the unique chord sequences for one of those subsets. Or what are the unique chords in such a subset? And this is shown here. This is essentially also a bookkeeping exercise, just trying to exclude chords which are only in one subset and not in the other. But much more interesting, but more difficult to obtain, is to understand which part of a song, in terms of n-grams, points towards which regional subset. No song is pure in the sense that all the bigrams in a song point towards the same subset. Here, for example, you can see by the coloring that the first two bigrams are colored in blue, so they point to the Shemok Medi subset. And from the size, you can see how certain the classifier is that this statement is actually correct. If the size of the labeling is very small, the classifier is not certain at all. Any of the other subsets might be just a little bit smaller. So when we go through this sequence, we see that then the third bigram, so this would be the transition from 045 to -135, points towards guria, but with a much lesser certainty. And it's even smaller, the certainty, for the next bigram, which points to katli kacheti. And it's the transition from -135 to -158. So from the size of the labels and from the corresponding colors, that you can immediately see that the most likely region of origin for this song is colored in blue, so it's coming from Shemok Medi. This is how the classifier actually works. Not all of the chords are pointing to the same subset, but this kind of display then actually will help us in the next step of our analysis to increase our own understanding, trying to find out what are typical chord progressions for one of the subsets. So I don't want to overinterpret this last example. It is just an illustration of the kind of tools that one can develop for subsequent analysis, which then will need to be done together with musicologists again. This is no longer than a technical question. So let me wrap up here. The purpose of this talk was to illustrate where we stand with our attempts to analyze the syntax of traditional Georgian music based on digital scores. We believe that we have now the basic tools in place which we need to make the next steps, but we need still more data if we want to exploit the potential of these modern analysis tools, for example from machine learning, AI and computer linguistics. However, the preparation of the scores turned out to be extremely time-consuming, and working under COVID conditions did not help either. We have to accept that the whole endeavor contains quite a number of steps. as illustrated here. So if you force me to say where I believe we currently stand, I would say roughly here. So we have still some steps to climb, but we already left the ground. So thank you very much for attention.